I'll record it, and if nothing interesting happens, I won't post the recording. But what about maze solving?
Well, I've heard of different algorithms for it. I've
Okay.
never really heard of one that was particularly efficient for the mazes that are called, what do you call it when there are looped paths in the maze? Disjoint or not disjoint?
Um, I don't know. I would have used the word cyclic or something, but maybe disjoint is a word that people use for it.
Hmm.
I mean, it on some level, it boils down to like shortest path, right?
If you could express a maze as a graph neatly, I suppose so.
Yeah. So I mean, I don't know how else to express a maze actually, right? It's like um, I'm gonna draw maybe the worst maze known to man. But oh, I can't draw a maze. What am I thinking? I'm gonna Google images a picture of a maze. Uh, and then I'm gonna, ooh, yeah, okay. I'm gonna screenshot this from Pinterest. Let's see if I can, there we go. Okay, excellent.
Whole upper
Okay.
half is completely unnecessary. Like no one would ever go there if you come in from the left.
That's true. Um, but we can think of, I mean, we can start by like discretizing this, right? And we can think of every point here, or think of this maze as existing on a grid, right? Every point is a vertex on a graph.
Huh.
And then there's edges every time a vertex is reachable from another vertex, right? In fact, we you can like um you only need to have vertices for like the places where you have more than one uh choice of where to go, right? So we could have a vertex here for the start and a vertex here for the end, which is fine. And then one here because you can sort of go down or to the right, and then maybe one here, and then one here, right? So you can kind of, I mean, you can overestimate, right, just by placing vertices along every like discrete point along the maze, or you can I mean, you'll end up with some sequences that just look like a line of vertices with edges and then stuff like this, and so you can kind of like contract all of these together into just a single vertex. Um, but you sort of uh, I don't know. Yeah, you can represent the graph in this fashion and then just do shortest path, right? In particular, you know almost by construction that this graph is planar, which means that like you have some decent heuristics uh for pathfinding, right? Like you can say like you can use A star by saying in general I want to move in this direction. Although of course the maze might force you to kind of go all the way back and around before ending up at the right spot. But you can kind of think about adding heuristics to this to make it better. But like fundamentally, uh, I don't know, a maze is a graph, right? It's a graph of choices that you can make of like where you go at each step.
True. Hmm. In this maze is not cyclic. Oh, very well.
Hmm. I
Hmm.
mean, even if it were, you would have a graph with cycles.
Hmm. Very well. You've solved the maze. Oh,
Sorry, I don't mean to try to like trivialize the
right,
um
right. How about Sudoku algorithms?
ooh, oh, I'm so happy. Okay, yes, let's do that.
Good to
So,
hear.
um Sudoku, okay, so perfect like Sudoku puzzles are interesting because there's guaranteed to be a unique solution, right? And it might not be the solution that any heuristics find. So you sort of have to like search intelligently. Um, uh, so let's talk about Sudoku, right? Um, on some level, you can think of Sudoku as a graph coloring problem. So I don't know if you remember what graph coloring is from maybe I mentioned it on Wednesday,
You did.
but okay. So the idea is you've got a graph with a bunch of vertices, and you want to assign values to each vertex such that two adjacent vertices never have the same value, right? Um, and you can think of a Sudoku board or a Sudoku like grid or whatever as being a giant graph where I'm gonna do like a 2 by 2 instead of a 9 by 9. Right, so here's your like boxes. Here's the like 2 by 2 cells in each box, right? So we've got 16 vertices. And we've got constraints that say that uh, everything in the same row has to be distinct, everything in the same column has to be distinct, and everything in the same format, like 2 by 2 grid, has to be distinct. So we just form cliques out of these, right? So we connect like everything in the row to everything else in the row, like that, right? And then sort of do this for every row, and then do the same thing for every column, right? And then also do it for every 2 by 2 um, like grid cell, which I guess these these edges become redundant. So I really just need these edges because the rest of these are going to get connected or whatever. But when you do this, you end up with a graph with just a ridiculous number of edges. Um, and then you can think about coloring the graph where the colors you choose from are 1, 2, 3, and 4, right? And then you notice that the coloring condition that says like two adjacent vertices can't have the same color is exactly what it takes to have like two things in the same row can't have the same number, two things in the same column can't have the same number, and two things in the same sort of box can't have the same number, right? So you can reduce. So I mean, this works for sort of an empty Sudoku puzzle, right? If nothing is filled in, you can fill things in based on this. Um, of course, the coloring you find might not match with like let's say you know that there's a 3 here and you know that there's a 1 here or something like that, right? The coloring you find might not assign 3 and 1 to these particular locations, right? Um, in this case, it only matters that it assigns like different things to these two. But let's say you've got like a 3, a 1, and another 1 here, right? So now whatever coloring your algorithm finds might not give the same color to this cell and this cell, right? So now you've got constraints, which means that graph coloring might not work as well. Um, and so there's like constraint solving uh, algorithms. Most of these, are you familiar with like complexity classes? Like if I say P versus NP, NP complete, NP hard,
The names
are
sound
these
familiar, but I couldn't define them.
okay? So they're classes of algorithm or they're classes of problems, right? So the usual diagram that people draw is like here's the class of NP problems, here's a class of P problems. Um, and then there's other stuff that kind of branches off of this that I don't want to mention. But P stands for problems that can be solved in polynomial time, or maybe problems for which there is a polynomial time algorithm. And NP stands for these are decision problems, by the way. So these are like these are problems where you have some input and then the output is either a yes or a no. So you can think about like, is this number prime, for example, right? Or is this is this graph three colorable? Um, or is this set of solutions satisfiable? Or is this set of like Boolean constraints satisfiable or something like that, right? So NP is problems that can be verified, or maybe problems for which a solution can be verified in polynomial time, right? So it's worth noting, first of all, that NP, like there's potentially problems that are harder than NP, right? So the N here stands for non-deterministic. Non-deterministic polynomial. Um, because the idea is if you have access to sort of a guess and check oracle, right, that can just like make an infinite number of guesses, or like it can like make a non-deterministic guess. So like yeah, if you have access to something that can like make a bunch of guesses for you, then you can check to see if any of those guesses are a correct solution in polynomial time, right? Which in particular means that there's always an exponential algorithm. Uh, for solving these. Just because you can sort of in exponential time enumerate every possible guess and then check each guess in polynomial time. And so the exponential dominates the time complexity. Um, Within here, there is a class of NP-complete problems. And these are essentially problems that are all like equivalent to each other. In a sense that I maybe won't make super precise right now. But the idea is if you take one NP-complete problem, you can transform it. Like you can always convert between NP-complete problems without changing the overall complexity or the overall hardness, right? So actually, maybe I will be a little bit more precise. There's polynomial time algorithms to convert from any NP-complete problem to any other NP-complete problem. And in fact, the way that you usually show that something is NP-complete is by demonstrating a polynomial time algorithm that converts from it to a known NP-complete problem. So um, the maybe canonical example of an NP-complete problem is the satisfiability or Boolean satisfiability, which you might see referred to as SAT. The idea here is you've got a bunch of Boolean variables like x0 dot 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 xn and a bunch of Boolean formulas, like a conjunction of Boolean formulas, right? So this would be like a conjunction of clauses where the clauses are themselves disjunctions, right? So this would be something like x0 or not x1 and x0 or x2 or not x3 and dot dot dot, right? And the decision problem asks, is there an assignment of truth values to such that this formula is true, right? So you can imagine on some level, this entails like checking to see if there's a contradiction, right? So if you ever have a clause that's just like x0, and then you have another clause that's just like not x0, then you know for a fact that there's no way to make this true, right? Because there's a contradiction, right? So you can immediately return false. Um, but this is the satisfiability problem. And it turns out that satisfiability is very powerful or it's maybe very expressive, right? So you can encode Sudoku as one giant satisfiability problem. Um, with the idea being um, you have you have variables that represent every possible value that a cell could be, right? So you have like um, x sub let's say 0, comma 0 equals 1, x sub 0, comma 0 equals 2, and so on. And then x sub 0, comma 1 equals 1, 0, comma 1 equals 2, right? So for every possible value that every possible cell might have, so in a normal like 9 by 9 Sudoku grid, you might have, what is this, 81 times 9, so 729 variables, right? Variables like x1 through x 729. Except some of these are already filled in. So you don't have the ones that are already filled in, right? So it'll be like 729 minus some k. And then you can express the all of the like the constraints of your Sudoku board as a giant clause like this, or as like a bunch of clauses like this, right? So for example, we can say like um, zeros like uh, the how do I want to say this? The value at 0, 0 equals 1, and the value at 0, 1 equals 1 can't both be true, right? So one of these has to not be 1, right? So we can build a sort of we can build a clause that represents this as a disjunction of variables, right? And this is fine, right? Um, and you sort of continue, and you get an enormous number of clauses, right? This is something ridiculous. It blows up. It's very much exponential, but you can think of any clever techniques that can solve stat will um, help you solve Sudoku. Will help you solve the Sudoku board. It turns out that if you've heard of like P equals NP, um, this is kind of uh, I don't know, it's like a Millennium Prize problem or something. Like
I believe so, yes.
yeah. So P equals NP. So basically we know that P is a subset of NP, right? Because anything that's polynomial, anything where you can find a solution in polynomial time, you can necessarily check a solution in polynomial time just by using your polynomial time algorithm to come up with a solution and then comparing them, right? But the question is NP a subset of P, right? In other words, for all of these NP complete problems, is there some polynomial time algorithm that we just don't know about yet, right? Um, and we don't know. Like that's sort of unanswered. So in particular, any NP complete problem, the best you'll be able to do is necessarily exponential time. Um, but you can on average do a lot better, and you can like on average reduce what that exponent looks like, right? So you can go from something like 3 to the n to maybe 2 to the n, or like 1.6 to the n or something like that. All of these are still exponential, but like this is way better than this, right? Um, so yeah. So there's a bunch of like heuristics. There's a class of programs called sat solvers, which are basically um, just a ridiculous number of heuristics and search procedures and stuff like that that know how to solve um, instances of SAT, right? And of course, it's still going to be exponential, but you can often the make the time like relatively small. Like you can often get some sort of efficient solution out of these. And there is like a ton of research that goes into and that probably still currently goes into like making these even slightly faster. Um, there is a particular algorithm called DPLL. Right. Okay. So first of all, like a naive solution, a naive way of solving this, right, is you've got n variables, right? So you just check like all of the 2 to the n. I mean, if you've got like x1 through xn, right? You just check all 2 to the n possible assignments, right? Of truth values, 2 to the n because each variable can be either true or false. So you've got like yeah, um, every subset of true variables. And you I mean, it's very easy given an assignment of truth values. It's very easy to check if it satisfies the formula, right? Because you just plug these things in, and as soon as one of these clauses is false, then you return false. If none of them are false, you return true. Um, so DPLL is basically this, but with a bunch of like pruning heuristics built in. So I'll say DPLL, which Wikipedia tells me stands for Davis Putnam uh, Logman and Loveland, right? So the idea with this is uh, there's two like subroutines here. Unit propagation. I guess unit propagation is the important one. Um, and I guess pure literal. Actually, maybe it's worth just screenshotting the pseudocode here. I was not prepared to talk about DPLL, but I'm very happy that I get to. Okay, so morally, what this is doing is basically a full brute force search, right? Because you like you choose some literal. So a literal is either xi or not xi, right? So it's either a variable or a negation of the variable. Um, and uh, you try assigning it to true, you try assigning it to false, and then you sort of recurse on both of these, right? So you choose a literal out of here, and then you sort of recurse on both of these, which is what this part is doing. But there is like this stuff, right? That shrinks that shrinks the size of the space that you have to search, right? So often you won't have to search the entire thing. But in particular, if you've ever got something like if you have an empty clause that's just like x0, or not an empty clause, but a clause with just one literal and something, we know for a fact that x0 has to be true, right? There's no other way to make this true, right? Um, so that's sort of pure literal assignment, right? So we can kind of we can get rid of this clause. We can shrink our formula by getting rid of that, and we can reduce the total number of variables by 1 because we know that x0 is now true, right? Um, and then similarly, if you've got something like you know, x0 or not x1 or blah, 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 right? And let's say we know that all but one of these is already set to false, right? So let's say we know x0 is false and we know x1 is true, and we know like if all but one of these has already been assigned, then we know that the last one has to be whatever makes it true, right? So maybe for example, x0 or not x1 or not x2, right? If we've already assigned x0 and x1, and we've assigned x0 to be false and x1 to be true, then this is false, this is false. So x2 has to be false, right? So we can go ahead and immediately assign it and propagate that assignment everywhere, right? So, I mean, fundamentally, what it's doing is searching every possible, like, uh, uh every possible way of assigning truth values to variables, but it can be smart about it sometimes by like finding situations like this, right? Um, and it, like if a clause is already satisfied, if a clause has already been made true, so if x0 is true, then there's no need to think about this anymore. So we can just get rid of it, right? Because we've reduced our formula to true and something, which is just the remaining something, right? So we can sort of very aggressively prune the number of clauses that we have and the number of variables that we have to make this not suck so bad. That's the idea. And then of course, the like the crux of making this actually good is like how do we choose the next literal to explore, right? Because we want to choose we want to choose something that's going to make as many clauses as possible disappear, right? Or that's going to allow us to make as much progress as possible, right? Like it would be great if we choose some L such that this immediately returns true, right? Because if this returns true, then we don't have to check this at all. So we've kind of like halved the size of the space that we need to care about, right? And so a lot of stuff goes into like um, finding good heuristics for this, which I don't know, I think is kind of funny, right? Like choosing the next literal to explore is maybe one of the most boring things that you can think about in a recursive algorithm, right? Like if you're sort of doing a depth first search of a tree or something like that, right? Like the thing you want to spend the least amount of time thinking about, at least for me intuitively, is like, okay, which neighbor do I explore next, right? That's like I'm going to explore all of them, so it doesn't really matter. But here it ends up mattering quite a bit because the only reason DPLL is not this like awful 2 to the n, I mean it's still pretty bad, it's still exponential time, but the only reason it's able to like return a value in a reasonable amount of time in most cases is because we've got these great like pruning things, right? Like we can propagate units and we can assign pure literals and stuff like that. And so it matters a lot how much we're able to prune at every step, right? So a lot of work goes into like finding good heuristics for choosing the next literal.
Mm.
And so a lot of SAT solvers, I mean, I think most commercial SAT solvers implement like DPLL plus their own custom set of heuristics. Um, and so in
Yeah.
particular, if I ever wanted to write a program to solve Sudoku, I think the way I would encode it is just as a giant SAT problem, which again, I'm sorry, is maybe unsatisfying. Like there's not a clever, there's not like a neat polynomial time algorithm that just always gives you a perfect answer. At least not one that I know of. But
Well, no, you'd probably have your thesis finished if you knew of that algorithm, yes.
yeah,
So, suppose it's convenient. Everything can be reduced to Boolean since it was zeros and ones to begin with.
Hmm.
Yeah.
It's very convenient. Um, there's, I mean, this is maybe anecdotal, but there's a lot of things in my research where I'm like, gee, I really wish I knew how to do this, or I really wish I had a convenient algorithm for doing this. And it turns out that the easiest thing for me to do is just kind of like naively or like dumbly encode it as just a giant sat formula and then import a sat solver and ask it to solve it for me. And it'll maybe take a couple of seconds, but that's way better than the like months that I would spend trying to come up with a more clever way to do it. Right? And it just works. Like it's just fine. Um, so yeah, NP-complete problems are cool. I mean, stat solvers are cool, I think. Do you have anything else that you want to talk about? I could go on
Um,
about more NP-complete stuff. I could give examples of other NP-complete problems. I could go back and talk about graph coloring algorithms. Uh, maybe
True.
this
We
is,
never did learn a coloring algorithm that I know of, just the definition of a coloring.
that's true. We didn't. Do you want to do that?
Sure.
Does that seem interesting? All right, let's do it. So I will preface this by saying I'll write graph coloring here. So disclaimer. Finding even so the question of um, is G K colorable is NP complete. Okay. So I'll start by saying that there's never going to like I'm not going to be able to give you a satisfying polynomial time algorithm for finding the minimal coloring, right? However, there are and of course this is the decision problem version of it, right? The thing that you might actually care about is what like it if it is, let's say, three colorable, what is a three coloring of G? Um, uh, maybe as a reminder, K colorable means is it possible to color this in with K colors? Um, but there are some like heuristic based algorithms that will not always return the best coloring, but will often do good enough, right? So
Best
um,
coloring?
that best is in minimal K,
Oh,
right? It
yes.
isn't it won't necessarily use the fewest number of colors, but it'll often be good enough, right? Um, so the uh, maybe the two algorithms that I'll describe here. I don't know the names of these. I just kind of okay. I'll describe the one that I use all the time without knowing the name of it. Um, uh, so you have a graph, right? Maybe this is a good graph. Yeah. Okay. So we start by okay, so first of all, vertices with a very low degree are intuitively very easy to color, right? Because there's very few constraints on what their color can be, right? So this vertex right here, there's only one thing that it has to not equal, right? Or the color of this only has to be different from this one. But the color of this one has to be different from that, and that, right? So maybe I'll start by saying like observation, low degree vertices are easy to color, right? Another observation, uh, fixing a color for a low degree vertex is relatively harmless, right? What I mean by that is if we I mean, on some level, we're going to have to do a search, right? We're going to have to search through possible colorings, and we're going to have to pick something, right? So if let's say we start by picking this as being red, right? This, of course, constrains the space of colorings available to us, right? Because now we know that this vertex cannot possibly be red. But that's the only constraint that coloring this applies, right? Whereas if we colored this one red, then we would apply a bunch of constraints, right? We would know that this one can't be red, we would know that this one can't be red, and that this one can't be red, right? So when I say harmless, I mean it reduces the space of viable solutions by very little, right? And because we're trying to find a solution, not the solution, reducing the space by very little is a good thing, right? We don't want to shrink the space too much because the more we shrink the space, um, heuristically, the less likely it is that we will actually find a solution, right? So the idea here is based on these two observations. Start by coloring low degree vertices. Okay. Of course, we can't just like we start by coloring low degree vertices, but we also kind of adjust the degree of each vertex based on what remains uncolored. So the actual pseudocode for the algorithm, I'll say we start by we initialize an empty stack. Okay. And then while G is not empty, we remove the highest degree vertex from G and push it onto the stack. Right? And we keep doing this. And so we've removed everything from G and we've pushed everything onto the stack. And now, while the stack is not empty, we pop a vertex off the stack, color it greedily, and add it back to G. Right. By color it greedily, I mean give it the first available color that works. Right. So as an example, let me redraw the graph that I drew above. Right. So we've got like this, and then we've got a triangle here. Right. So maybe it's worth naming these vertices. So we'll call this A, B, C, and D. Right. So we start by pushing B onto the stack. Right. So we remove the vertex B from our graph, which means that the resulting graph is just disconnected A and then E and D, right? Now and we push B onto the stack. Then we push, let's say we push C because C and D have the same degree. We push C, and that leaves, oh, that looks like here we go. A and D, just two disconnected vertices. Now we can push D and push A, right? It doesn't really matter what order we push these in. And so now our graph is empty, right? So now we pop A and color it, I don't know, color it red, right? So now we've got a red A in our graph. Now we're going to pop D. D is also not connected to anything yet, so we can color it red. right? We're just giving it the first available color. Now we pop C. C is now going to be connected to D. So we can't color it red because it can't be red, but we could color it blue. Right? So we can color, maybe I'll draw the edge in black and then I'll draw C in blue. And then finally, we can pop B and it's going to be connected to A, C, and D. So in particular, it can't be red, it can't be blue. So let's color it green. Right, so I'll put B here, and then I'll draw all of the edges, right? And so now we've colored this graph with 3 colors. In this case, it turns out 3 is the best we could do because we've got this like triangle here, right? Which in particular is like a copy of K3, or a complete graph on 3 vertices. And so anytime you have a complete graph on n vertices, you need at least n colors because every vertex of that complete graph has to have a different color, right? So
Yes.
we know that 3 is the best that we could possibly do, and we have a 3 coloring. Now, of course, like removing vertices, like deleting edges from the graph, and then like trying to add the vertices back is a neat way to like conceptualize it or draw it, maybe, but not the way you probably want to implement it, because especially if you're writing this in C, like I don't know, pointers are very messy if you try to do this. So maybe the way you want to think about it is you order the vertices based on their, or like you push vertices onto the stack, and then when you're calculating the degree of a vertex, you only look at the degree of a vertex that's not already on the stack. And then when you color things, you color from the top down, and you only look at conflicts on you only look at conflicts for colors that are above it. You only look at conflicts for vertices that are above it on the stack. And so you don't actually have to like change your physical graph data structure, but you can kind of pretend that that's what you're doing, right? So this works. Does that algorithm make sense? So
Yes,
this
it
will sort
does.
of greedily try to find as few colors as possible, but it might get it wrong. Like there might be a better, I mean, in this case there isn't, but there might be a better coloring available that this algorithm doesn't find. The other one, which I don't often use in practice, but this kind of instead of going vertex by vertex, this goes color by color, right? So proceed color by color. And this is basically find uh, a maximal independent set of vertices, color them all the same, and then repeat. So here, by independent set of vertices, like an independent set is a set of vertices where no 2 vertices are adjacent to each other, right? So, in fact, here I think this would produce the same coloring because the only independent set of size 2 is either you could look at these two or you could look at like AD or AC, right? Are 2 vertices that are not adjacent to each other. But anything else, like if you picked AB, for example, AB are adjacent. If you picked B with anything, B is adjacent to everything, right? So the only independent sets of size 2 are AD and AC. So we pick, let's say AD, we color them both red. Now we look for the next independent set that doesn't contain A or D. So we find just a singleton C, we color it blue. We look for the last remaining one, which is just singleton B, we color it green. Unfortunately, uh, identifying, um, actually, is this true? Hang on. Yeah, yeah. Uh, Finding independent sets is NP complete, right? So here you use your favorite like heuristic for finding independent sets, right? So maybe you start by picking a vertex that has like a very small degree, and then you remove it, and you find a vertex that has a very small degree in what remains that's not connected to it, right? So we start by picking A, and then we pick something that's not connected to A. So maybe we pick like D, right? And then we pick something that's not connected to A or D, and we find that there's nothing else that we can pick. So we're done, right? So we sort of greedily build up this independent set. It's not guaranteed to be maximal, but it will give us an independent set, and we can color it, right? And then we just color it the first available color, right? So this also works. It's also not guaranteed to give you the best possible coloring because any nice algorithm that I can describe is not going to necessarily give you the best possible coloring because coloring is NP-complete. Um, but it is often good enough. Like it'll often give you something good enough. Does that make sense?
Yes, it does.
Cool. Do you have other questions about any of this or about anything else?
Hmm. Let's see. When we first discussed graphs, it was mentioned that there were infinite graphs and that our algorithms usually broke down on those. Are there any algorithms you know of to do things that do work on infinite graphs?
Yeah, so um, you can often adapt things that you care about to work on infinite graphs, right? So for example, um, let's say Dijkstra's, right? Dijkstra's on an infinite graph. So obviously, the first constraint is we can only explore things uh, a finite distance away, right? So we can only look at like a finite slice of the infinite graph because it doesn't really make sense. Like, what's the shortest path between here and a vertex that's infinitely far away, right? Um, and the other thing is we need the graph to be locally finite. This means that the degree of every vertex is finite, right? So you never like you might like so for example, an example of a locally finite graph is a locally finite but infinite graph is like the infinite path graph, right? So there's a vertex for every natural number. There's an edge from I to I plus one. Um, but the degree of every vertex, like every vertex has an in degree of one and an out degree of one, with the exception of zero. Um, so it's locally finite, right? So you can still run Dijkstra's on this. Um, it's just your loop won't terminate. So you have to force it to terminate when you find something that you care about. And you have to be careful with how you write it, right? So um, one way of conceptualizing Dijkstra's is you give every vertex a distance of infinity, and then you put them all into a priority queue, and then you use this like um, decreased priority operation on the queue, right? Every time you open a new vertex, its distance becomes finite, and so you move it up in the queue. You can't do that anymore if there's infinitely many vertices, so you have to adapt your algorithm to sort of build this priority queue as you go. But that works just fine, right? I feel like a lot of other things that we talked about were search algorithms. Um, and the same sort of thing applies. Like as long as your graph is locally finite, your loop won't terminate. Um, but you can add an extra termination condition to sort of force it to stop when you found something that you care about. or stop after a certain number of vertices have been explored or a certain radius has been explored or something like that. Graphs that are not locally finite are just cursed. Like yeah. Good question though.
Thank you.
Does that I don't know, does that answer what you were asking sufficiently well, or is there something
Uh,
missing from that answer?
the other question was vague. Is there something we can do with infinite graphs? The answer is yes, if they're not too infinite.
Hmm.
That answered that. Okay, I suppose I have one question that'll be the last one because I think it's the most, well, if there is an answer for it. So, we've described in class, I think, with that checkers example, an AI of sorts that considers everything to be a graph. But pretend for a moment we're not really calling it a graph. That AI will recursively look at every possible move player one can make and every move player two can make back and forth recursively for a while. And I think
Hmm.
that could probably solve really any turn-based game. I've done it myself
Hmm.
for dots and boxes online. Wondering,
Hmm.
are there any other really general uh, ways to make a gaming AI that aren't the same simple recursive thing?
So I assume you're not asking about like ways to make this recursive thing better, right? Because there's pruning things that you can apply where you sort of don't bother exploring a certain state because you know that it's going to lead to a loss. Um, any deterministic two-player game or any deterministic like n-player game in general um, is solvable by like thinking of it as a giant tree. Other sorts of games, let's see. I mean, there's always like reward-based stuff, right? So sometimes you have like I don't know, softer games that aren't necessarily as deterministic. Um, but you've got like an environment to explore and you've got like different things that you might want to care about. And so uh, a thing that people will sometimes do for AIs for that sort of game is like uh, assign rewards to each um, action that the AI might take, and then kind of go based on that, right? Or you might consider like building a. I mean, I'm going to say tree, but I'm not referring to this in the like searching through a graph sense. But you might build like a tree of possible like decision like a decision tree, right? You might build a decision tree of like possible um, actions that the AI might take given what its current state is, given what its current environment is, um, and then based on that, it 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 reads the environment, uses the decision tree to sort of classify its environment into a particular result. It acts based on that result, and then um, pushes that action back into the environment. The environment changes, and you kind of like loop this procedure again and again, right? That's another very, I mean, that's maybe so generic as to not be very useful, but I mean, that's maybe another class of ways to solve or ways to write AIs.
I like that. That did answer the question very well. There's another
Oh, cool.
completely discrete way. You have to pick the rewards, but yeah.
Hmm.
Yeah.
I
We
mean,
are
so much of
coming
it
up
comes
on
down
the
to
end. Yeah.
domain knowledge. We are, that is true. Um, so if you have any last minute questions, I'm still around. But if not, thank you for showing up to literally every lecture.
Well, I missed a couple for work meetings, but I tried my best.
Oh, really? I didn't know that you had missed any.
Oh,
Uh, well, anyway, uh, this is great. This has been a ton of fun.
well, thank you. Thank you. I enjoyed it too.
I'm glad.
Mhm. Uh,
All right, if there's nothing else, I suppose you're free to go. I know you